Let's try to multiply these. Today we are going to talk about inverses and some pretty interesting stuff. Okay, so 2 by 2. This one would be a 2 by 3. So the first thing we have to check before we multiply is, can we do it? Yes, we can. The dimensions of the answer will be 2 by 3. So I'm expecting the answer to be a 2 by 3 matrix. So I've got kind of like, 2 by 3. So those are where my answer is going to go here. And again, we're going to multiply the row by column. So always the row in the first matrix, always the column in the second matrix. So if I want the top left, I'm going to do the top row and the left column. So first times first, 1 times -2 is -2, plus 0 times 5 is 0. So that first top left-hand term would be -2. When I do top row, middle column, that'd be 3, because 1 times 3, plus 0 times anything is 0, so we get 3. And the last column, it would be 1 times -4, so -4 plus 0 times anything, 0 times 7 is 0, so we get -4. Okay, let's do the bottom row and first column here, so that would be 0 times anything is 0, so 0, plus 1 times 5 is 5, so that would be 5. And middle column, 0 times anything is 0, plus 1 times -6, so -6. This one's pretty easy to do. And then 0 times -4 is 0, plus 1 times 7 is 7. And so we get our answer. I don't know if that surprised you or not, but one thing you may notice if you're paying attention is, let me just kind of like erase some of this just so you can see it better. Does this matrix look familiar, right? That's, I guess, the question. Does this matrix look familiar at all? Is it pretty much exactly the same as that matrix? It is. It's the same matrix. So multiplying by this matrix right here is kind of like when we do, 5 times 1 or something, right? Or 6 times 1. Multiplying by 1 doesn't really do anything. Multiplying by this guy right here, square matrix, has those 1s and 0s, doesn't really do anything, right? Just kind of, you get the same answer you started with. Let's try this one, see if this one works. First of all, does it even multiply? So this would be a 2 by 3 times a 3 by 3. So can we do it? Yes, we can. The dimensions of the answer are going to be a 2 by 3. So we're going to have a 2 by 3 as our answer. So we're going to have the matrix is going to have that kind of a look to it here. So the top row, when you do this, there's so many zeros here. You'll see what happens. It's going to be 1 plus 0 plus 0. This one's going to be 2, 0, 0, 3, 0, 0. When you do this one, it's going to be 9. Only the first number makes a difference. Only the second number here makes a difference. Only the third number, because all the rest are zeros. And so you end up with the same matrix here that you started with here. In other words, multiplying by this guy right here, it's kind of like multiplying by 1. So this has a name. It's called the identity, and we're not going to multiply this out, but do a guess, this is going to be our answer, right? It's going to be that. This is called the identity matrix. It's always a square matrix. That's why it says n by n. The main diagonals, you'll always see this pattern. The diagonals are always 1. All the other numbers are zeros, and it's the left top to bottom right diagonal that we're talking about here. All the other entries are that. So if I wanted to be cool and label this, I could call this the I sub 4 matrix. I could call this one the I sub 2 identity matrix. I could call this one the I sub 3 identity matrix, because those are the dimensions of the matrix. You don't have to know that name. You do have to know that, this is the identity matrix, and you'll see this. In this section, we're doing inverses, and identities have to do with inverses here. You'll see that in a second. So to test and see if a matrix, to test a potential inverse matrix. So first of all, it's got to be square, right? If there exists an n by n matrix where there's an inverse, if you multiply the matrix times, this is its inverse, so a matrix times its inverse, or the inverse of a matrix times the matrix, you will get the identity matrix. So if you multiply two matrices and you get, mysteriously, the identity matrix, you have discovered that those two matrices are in fact inverses of each other. So that's one way to discover if two matrices are inverse. So these don't look like inverses necessarily, like they're both 2 by 2 though, they're square matrices, so they might be inverses of each other. So if we multiply them, let's see what we get as our answer. So certainly 2 by 2 times a 2 by 2, we're going to get a 2 by 2. So right away, I know, we're going to have, that's going to be what our answer is going to look like. Okay, so let's do this. So we get 4 times 3 is 12 plus 11 times negative 1 is negative 11. So that first cell in the top left will be 1. Well, that could be the identity matrix. Let's see. 4 times negative 11 over 2 is negative 44 over 2, which is negative 22, I believe, plus 11 times 2 is positive 22, which is 0. So far, it could be the identity matrix. Let's see. 2 times 3 is 6, plus 6 times negative 1 is negative 6. This is looking good. And let's do the last one. It's hard to do that fraction. So 2 times negative 11 over 2 is negative 22 over 2, which is negative 11. And then 6 times 2 is 12. Negative 11 plus 12 is 1. Guess what? This is the identity matrix, which means if this is matrix A, this is the inverse of A, or vice versa. They're inverses of each other. We've just proven that they are because the product is the identity matrix. Now we can actually find it. There's a formula for finding the inverse of a matrix. And so if you have matrix A, B, C, D, so if you start with that, it's just 1 over the determinant of that matrix times, and this is kind of weird. They kind of they flipped around the A and D here. They changed that, and they negated the B and C. They changed the sign of the B and C term, and you multiply, and that's going to be the inverse. So we're just going to apply this formula right here. You can go right down in your notes to this problem. So it says the inverse of this one. So we're going to find the inverse of this. I'm just going to write it this way. So the inverse of that is going to be 1 over the determinant. The determinant would be 4 times 6, if you remember how to do that from the previous lesson, minus 2 times 11. Times, according to the matrix, we're going to flip around the 4 and 6. So this can be 6 and 4. We're going to negate or change the sign of the 11 and the 2 here. And then we're going to try to multiply this out. So this is 1 over, let's see, that's 24 minus 22, which is 2. So 1/2 times 6, negative 11, negative 2, and 4. And so if I do that, I get, let's just multiply that out. So 6 times 1/2 is 3. You get negative 11 halves. You get negative 1, I believe. Yeah. And you get 2. And so I think the inverse, that this matrix and this matrix are inverses of each other. In fact, if you look back at your notes, 4, 11, 2, 6, 4, 11, 2, 6, oh, like 3, negative 11 halves, negative 1, 2, 3, negative 11 halves, negative 1 and 2. Those are the matrices we just tested. They are, in fact, inverses. So we found the inverse of the matrix using the formula to find that inverse. So find the inverse of this one. So just make sure you know the formula. So to find the inverse of this one, so I'm just writing it like that, so I know to find the inverse. So this is going to be 1 over the determinant, which is 3 times 9, minus 7 times 4, times, I'm going to switch the 3 and the 9. I'm going to negate the 4 and negate the 7. I'm just changing the sign of those. So this would be 27 minus 28. Oh, that's just 1. So nice. So 1 times anything is just, the answer is just 9, negative 4, negative 7, and 3. And this is what the inverse will be. Find the inverse of this one. Okay, so we're going to do 1 over the determinant, which is 2 times 6 minus 3 times 4. Right away, let's just simplify that. 1 over 12 minus 12 is 1 over 0, which is undefined. So here we're learning something. There is no inverse here. So not all matrices, not even all square matrices, it has to be square matrices, have an inverse, but not all square matrices have inverses. So be careful of that. So there are some that just don't have an inverse, and this one doesn't have an inverse. 3 by 3 is a little tougher. So this is what I'm going to tell you on this one. So I'm going to go through the steps. You don't have to write these down. This will only be an extra credit question, but this will be an extra credit question on the test without a calculator. You have to show all your work. And unlike a normal extra credit problem, I think I normally give about 2 points for extra credit question. I'm not going to give 2. I'm not going to give 4. I'm not going to give 6. I'm not going to give 8. I'm going to give 10 whopping points on the test. So if you get this one extra credit problem right on the test, it'll be at different numbers, but it'll be a 3 by 3, say find the inverse. Then I will give you 10 bonus points. But here's the thing, everything has to be correct. So it has to be correct. So there's the first step, find the minor of each element. Okay, so to do that, it's kind of a weird step here. So we're going to, you kind of like, okay, so let me kind of just give me kind of a template for, I'm going to have a 3 by 3 here, 9 different cells in here. Sometimes I like just have that just so I can kind of keep my work organized so you know kind of where I'm going. So we're going to find the minor of each element. Okay, so the way to find that top left-hand term is it's kind of weird. You kind of circle that. Essentially, you're crossing out row and column, and you're left with a 2 by 2 kind of left over there. Find the determinant of that. So the determinant of that would be -1 times -3 is 3, minus 1. 3 minus 1 is 2. So that's the determinant of the leftover there. Now we're going to, so hopefully you have a good eraser here. Maybe you have to write those, and I don't know what you're going to do here. So the top middle is you're at least mentally, you don't have to cross them out, you're at least mentally crossing out row and column that term is in. There's kind of like a 2 by 2 left over there. So 1 times -3 is -3, minus 2 is -5. So I get -5. You have to be very careful about your math here. It's really easy to make a mistake. You get 10 bonus points if you get this right, though. That's huge. Huge. 110 on the test. You get a 90, it's now 100. 80 is now 90. It's huge. Okay, so this one, cross out row and column, you have a 2 by 2 left. 1 minus -2 is 1 plus 2, which is 3. Hopefully I do this right. Okay, so let's do this. So this one, cross out row and column, you're left with a 2 by 2. 3 minus 2 is 1. The case where the smartboard really does help do this a little faster. -6 minus 4 is -10, I believe. This one, row and column, so 2 minus -2 is like 2 plus 2, which is 4. Okay, this one is bottom left, so I'm crossing out row and column there. So -1 minus -2 is -1 plus 2, which is 1. I hope I don't make a mistake. It happens sometimes. Okay, so row and column, 2 minus 2 is 0. Okay, got a 0 there. And we get -2 minus -1 is -2 plus 1. -2 plus 1 is -1. Okay, so that's the first half, the first step. Then you find the cofactors. So the cofactor is a certain kind of matrix. So what we're going to do is, like if you think about those 9 cells, I think this is true. So I'm doing this from memory. We'll see how this works out. So it doesn't mean these are all positive. What it does mean is this. It means, so the top middle term, the middle left and right terms, and the bottom middle terms. Those terms, I'm going to change the sign of whatever they were. I'm going to change the sign of them. So that's what this cofactor is all about. It's just changing the sign of certain terms. If they start out positive, I'll make it negative. Okay, so here, this term is going to be positive now. It was negative. This is now negative. This is now negative. 0 is still 0 because it's not really positive or negative. Right, so I change the sign. So that's the end of the first step. So first we found the minor, doing that for each problem. Then we found the cofactor. We're done with the first step. Wow, okay. Second step, transpose row and column. This actually, it's not that bad. Okay, so we're going to kind of transpose that. So this step, we're going to, every row becomes a column, every column becomes a row. So the top row is 2, 5, 3. Now that'll be the first column, 2, 5, 3. The second row is -1, -10, -4. So that'll be my second column, -1, -10, -4. This isn't so bad. And then 1, 0, and -1. Okay. I think this might be the last step. Multiply the that by the determinant of the, I'm going to say it this way, of the original matrix here. So if you take this original matrix and find its determinant by hand, again, you have to do this all by hand. So let's find the determinant of this original here. So I am going to find the determinant of the original, doing the, remember the diagonals method? So the diagonals method, so what that is you copy down the first two columns here. So 2, 1, 2, -1, -1, 1. Okay, we're going to do diagonals here. So let's do those. So we get -2 times, that'd be 3, +3 times 2 is 6, plus -2 plus +2 is 6. Let's go the other direction here. So diagonals this way. So we get 2, that'd be 4 times, that'd be -4 plus 2 plus, again, hopefully I do this all correctly, 3 equals 5 plus -4 is +1. So I do the diagonals this way first. So 6 minus 1 is 5. Okay, so that's the determinant of the original. So I'm going to multiply this matrix times 1/5 times that, right? Because 1 over the determinant there is our method. So the answer should be, let's see if it is. Okay, so the answer should be 2/5, 5/5, which is 1, 3/5, -1/5, -10/5, which is -2, -4/5, 1/5, 0 times anything, 0, and -1/5. So the only way on the test to check this, to see if you maybe did actually do this right, I have no idea right now, is you can take the original matrix, multiply it by this matrix by hand, and make sure you get the identity matrix. And that would give you the answer. I'm just going to check it here because I have no idea if I did this right. So I'm going to type in, this is not something you do on the test, but I am going to check it here. So I'm going to do a 3 by 3. So 2, -1, 2, 1, -1, 1, and 2, 1, 3. And I'm going to find its inverse. 2, -1, 2, 1, -1, 1, and 2, 1, 3. Oops. So this is, whoops, no, I cancel. So, uh, so if I had erased this little piece right here, I would see that that's actually a -3. So when I typed it into the calculator the first time, I did not put a negative in there, but I'm going to put a negative in there this time, and I get this is my answer. Let's double check and see if that works. So I just typed it in without the negative because that blue line was covering it up. Easy to make a mistake here. And 1/5, -1, -2, 0, 3/5, -4/5, -1/5. We did do it right, in fact. So that is the correct answer. Again, if you do this correctly, you can check it. And this can take a little time on the test. But again, 10 bonus points, is it worth it? Take a shot. It's always impressive if you can do that. So every year I have quite a few students get it correct. And then I have the occasional student who gets it almost correct, like all but one cell maybe is correct and gets no points. So be prepared that that can happen, but if you do get it correct, you get 10 bonus points. So that's pretty huge. Let's go to this one real quick. I really like this question. I want to make sure you do it. So try this. Which one has the minimum value here? So stop it, make your guess. The most common wrong answer here is this one. Minimum value, if you remember to our formulas, y equals a times x minus h squared plus k. This is our vertex form. So the minimum of parabola would be the vertex, or h comma k. So right away, I know the answer is going to be one of these guys because these are the only two in vertex form that would have the minimum. The minimum is the k value. We're looking for which one has the k value. What is the minimum of this function? You can see by multiplying these, the y-intercept is -24. That means it crosses the y-axis at -24 somewhere down there, which means the minimum, the very smallest value, must be that or smaller. So the answer must be D. You can also complete the square to solve this, put this in the right form there. But oftentimes in this type of environment, so it doesn't say like which equivalent form. This is an equivalent form, so that's why it's so tempting. It is equivalent, but it doesn't show the minimum. The minimum of this function is -25. If you're able to use your calculator, you could graph this guy. Just see real quickly. I'm not sure if this is a calculator question or not, but if it was, you could definitely graph it. So this would be x plus 6 times x minus 4. And if you kind of trace it here, so if you go menu 5.1, you see the y-intercept is -24. The lowest value there does look to be, the minimum is -1, -25. So the very lowest point is at -25. That is the minimum of the graph, which is what the question asked for. So that'd be another way to do it if it was a calculator question.